In this module, we're going to look at two random variables that are continuous, and we're going to learn a lot of new things from that. Now, I know that in the previous module, we had looked at two random variables also, but they were discrete. Now we are going to deal with multiple integrals, and not everybody has practice with that, and so this will be quite essential because continuous random variables, 2, 3, 4, are what one must deal with in real life. We're going to not only deal with the mathematics, but we'll also look at certain joint probability distributions that are pretty obvious, and so we'll take examples of that. One particular example will be, I think, very interesting for you. This relates to an 18th century problem by a Frenchman called Buffon, and it's about dropping needles onto the floor. It's called the Buffon needle problem, and very interestingly, the number pi comes into this, and so if you do a random experiment, maybe you can find the value of pi. We'll come to that in a bit. At the very outset, let's consider two random variables. We will consider a sample space. This sample space will have an infinite number, in fact, an uncountably infinite number of events. That event, for example, could be an aeroplane which is flying at a certain speed at a certain height. Now, let x be one random variable, y the other random variable. X can take the value x, y can take the value y. X will denote speed, y will denote height. The joint probability distribution of x and y is the probability that x takes the value x and y takes the value y. So this is to be denoted as this, or making it a bit shorter, p of x, y as a function of the values x and y, and sometimes we make it still shorter, but they all mean the same thing here. In words, p of xy dx dy is the probability of finding an aircraft with speed in this interval, that is between x and x plus dx, and which is flying at a height in this interval, y and y plus dy. Now, in general, these two will be correlated. In other words, p of xy is not a function of x multiplied by a function of y. That's actually pretty obvious. Those that are flying at a greater height tend to move faster. So you could say that there is a positive correlation there. However, when the height becomes too great, then the speed can come down. And so the correlation will depend upon where in the target space one is. All the concepts that we studied for discrete random variables hold identically for continuous random variables, but there's a small change that has to be made. So let's recall how some basic formula need to be slightly changed or adapted. The most important thing is that the sum of probabilities must add up to 1. This is for the discrete case. For the continuous case, all we need to ensure is that the double integral of this function, p of x, y, that is the joint probability distribution, that integrates up to 1. Now here, the integration is over all values of x and y. So strictly speaking, this integration over x goes from minus infinity to plus infinity, and similarly this integration over y goes from minus infinity to plus infinity. But it is often the case that this function over here, the joint probability distribution, is 0 for most of the values of x and y, and so therefore this integration will be carried out over a limited region. We'll see many examples of that very shortly. For discrete random variables, we sum over y to get the marginal probability distribution in x. Well, for the continuous case, all you do is instead of the sum over y, you do an integral over y. And here, x is held fixed in this integral. The integration is over y. Where does y start from and where does it end? That we shall see in various different examples. Similarly, if you were to sum over x in the case of discrete, well, then you're going to integrate over x in the case of a continuous function here. Now, if you want the expectation value of xy, then that is, in the case of discrete, a sum over x and y, whereas over here, in the case of a continuous distribution, the expectation value or the average value of xy is the value taken by x times the value taken by y weighted by the joint probability distribution function and then integrated over all values of x and all values of y. And these integration limits over here are, of course, the same integration limits as over here. Now the covariance of x and y, as before, is defined exactly as you would expect. So it's the average value of xy minus the average value of x into the average value of y. In fact, it is now pretty obvious, boringly obvious, that if you have a function of the random variables x and y, any function, this could be a polynomial, this could be sine, cosine, anything, well, x takes the value x, y takes the value y, so the function of x and y weighted by the joint probability distribution function, well, you sum over x and y. In this case, all you do is you integrate over x and y. There can't be anything more obvious than that. But then what we need is a bit of practice in doing multiple integrations. As our first simple example, let us take the random variables x and y, which have the joint probability distribution x plus y, where now x is limited in its range. It doesn't take all values. It's in the range 0 to 1. Similarly, y is in the range 0 to 1. First of all, is this joint probability distribution that I've written down actually qualified to be called a joint probability distribution? We'll have to check that. So we must check the normalization of this. Although we can do that without drawing any kind of diagram, it is always good to have a picture before us. So here is the xy plane. X is in this direction, of course, y is in this direction, and what we need to do is work out this integral dx dy over x plus y. Now, let's be explicit about the integration limits. And so what we are actually looking for is the integral of y from 0 to 1 and the integral of x from 0 to 1 of this function, which is x plus y. In terms of pictures, dx is the thickness of this strip here, and dy is the thickness of this strip here. So this is at constant y, whereas this is at constant x. This square over here of thickness dx and dy is the little bit of area, and so basically what we're doing is adding up all the little areas over here weighted by the probability distribution function x plus y. You could ask, could we have dx over here and dy over here? The answer is absolutely yes. There will be no difference in terms of the answer. But now let's proceed with the integration. This first integral over here, let's do the integral over x of x. That is half x squared between the limits 1 and 0. So that's just equal to half. What about over here? Dx into y. Y is a constant so far as x is concerned. So when we integrate dx, this is like dx into 1 multiplied by y. And so that gives xy with x going from 0 to 1. And that simply gives you y. So this first integral, this inner integral, gives half plus y. Now you can integrate over y, and if you integrate half over y, you get half. And if you integrate y, well, you get y squared over 2, and that gives you half as well. So you get half plus half, and that's equal to 1. That's the way it should be. If you reversed x and y over here, again, of course, you would get 1. Now let's come to the first part of the problem. Find the marginal distribution px of x. What that means is we need to integrate over y holding x constant. Now just put in the integration limits. The integration limits on y go from 0 to 1, and we're integrating x plus y. When we integrate this term, x is just a constant so far as y is concerned, and so we will get y between 0 and 1, which gives 1. When we integrate this, we get y squared over 2, and that's between 0 and 1, and so of course we get x plus a half. Let's now repeat this for y. So now we need to find this marginal probability distribution, in which case we need to integrate over x, and of course it's exactly identical. The difference is that you're integrating x from 0 to 1, the same function x plus y, and of course you're going to get y plus a half. Now notice over here that p of xy is not equal to x plus a half into y plus a half. In other words, this joint probability distribution, x plus y, is not equal to a product of something which is only a function of x times something which is only a function of y. That was fairly trivial. Now let's go on to ask, what is the probability that the random variable x plus the random variable y take values which are less than 1? In other words, in this region where x plus y is less than 1. Well, of course, if x plus y is less than 1, that means that x is less than 1 minus y, and it is best to picturize this. So here is what the picture looks like. If one takes x plus y equal to 1, or you can write y is equal to 1 minus x, or x is equal to 1 minus y, well, that is this line over here. X plus y less than 1 is this region here, the shaded region, and the region x plus y greater than 1 is, of course, the unshaded region, this white uncolored region here. We now need to work out this double integral over here to get the probability that x plus y is less than 1. So for this, let's go to this diagram here. X will be integrated all the way from 0 to 1 minus y. So whatever the value of y is, and we know that lies between 0 and 1, x will then go from here all the way up till here. So let's come back to this integral now that we have the limits. Well, if we integrate x, we get x squared over 2. If we integrate y, we get y into x. And now the limits of integration are 0 to 1 minus y. Just put those in, and instead of x, you're going to get 1 minus y, so we have half into 1 minus y squared. This lower limit does not contribute, and similarly over here, xy will give us 1 minus y into y. Just simplify this. You can see pretty clearly that this over here is half minus y squared over 2. Well, when you integrate half, you're going to get half. And when you integrate y squared, you're going to get y cubed over 3. And that taken between 0 and 1 will give you 1/6. So you have half minus 1/6 coming from this term over here. That gives you 1/3. So we've successfully calculated that the integration over this shaded region, the blue region over here, gives 1/3. You can now ask the question, what is the probability that x plus y is greater than 1? Actually, we already have the answer because the total probability has to be 1. So it's 1 minus 1/3, which is equal to 2/3. But let's just check if this is actually what we get upon calculating this directly. So the only difference is that now x will go from 1 minus y to 1. Look over here. This is x equals 1 minus y, and this here is x equals 1. So x gets integrated over this distance here. Again, as before, the integral of x dx gives you x squared over 2. Evaluated between the limits 1 and 1 minus y, that's half minus half 1 minus y squared, which comes from this lower limit. And for this term, we will get y into x, where x goes from 1 minus y to 1. So the integral gives you y. That multiplied by this y gives you y squared. And if you simplify this, that's y plus half y squared. The rest is pretty trivial. If you integrate y between 0 and 1, you get half. If you integrate y squared between 0 and 1, you get 1/3. So that's half plus 1/6, which is equal to 2/3. And so, indeed, 2/3 plus 1/3 is equal to 1, as it should be. Let's take a second example. Here again we have two random variables x and y, but they have a different joint probability distribution, which looks a little strange. Here we have the joint probability distribution equal to 1 over y if y is between 0 and 1. Now note that there's no x over here. However, there is implicitly x present because x has to be between 0 and y. So, as y changes between 0 and 1, x will remain below y. If this condition over here is not met, then the joint probability distribution is equal to 0. In this question, we are asked, first of all, to find the marginal probability distribution in y. So, of course, you get that by integrating over all values of x. Here, y is to be kept constant during this integration. And now the question is, where is this integral being evaluated? In other words, what are the limits here? I remind you that if y is negative, or if y exceeds 1, then, of course, the probability distribution in y will be 0. So getting this was trivial, but now let's calculate what the marginal probability distribution in y is when y lies between 0 and 1. So now we have to integrate over x. But where does x go from? As we can see over here, x has to be bigger than 0, so it must start from 0 over here. However, x has to be less than y. And this y, of course, is between 0 and 1. We can do this integral trivially because this is just dx between 0 and y, and that gives you y. Y divided by y is 1, and so we have an answer. Py of y is equal to 1 if y lies between 0 and 1. And of course, it's completely obvious that the integral of p of y from 0 to 1 is 1. That was trivial, but now let's go on to finding px of x, the marginal probability distribution in x. Here, of course, we have to integrate over y. Again, if x is negative or x is bigger than 1, then by this condition over here, the marginal probability distribution in x will be 0. However, if x is between 0 and 1, then let's see what happens. So we have to integrate over y. Now, y will go from x all the way up till 1. That's because x has to be less than y, or equivalently, y has to be greater than x, but of course, it has to be less than 1. So dy over y, everybody knows that, that's log of y. And if you take log of y with the limits x and 1, you get log of 1 minus log of x, but log of 1 is equal to 0, and so this is just equal to minus log of x. Now this minus over here is somewhat scary because we're always used to thinking of probabilities as positive, and of course it is positive because if x is between 0 and 1, then the logarithm is negative. So negative into negative is positive, and so that's fine. The marginal probability distribution is positive. Of course, every probability distribution has to integrate to 1, and so let's check that. We need to integrate this. What are the integration limits on x? 0 to 1. Remember that there is no y anymore. Y goes from 0 to 1. Well, those are also the extreme limits of x, 0 to 1. Okay, now we need to know how to integrate log of x. Well, here is the answer. If you integrate log of x, you get x log x minus x. How did I know that? Easy. Just differentiate this. So if I differentiate x, I get log x only. Then if I differentiate log x, I get x into 1 over x, which is 1. And if I differentiate this x, I get 1 also, so that gives 0. And so, in fact, the integral of log x is x log x minus x. The integration limits over here are from 0 to 1. When I put x equal to 1, I get 1 log 1, that's 0 because log of 1 is 0, minus 1, that's this x equal to 1, and so that minus into that minus is a plus. What about the lower limit? No problem over here, but here I have 0 log 0. Well, what's 0 log 0? Log 0 is, of course, minus infinity, but this x log x is equal to 0 as x approaches 0. You can use L'Hopital's rule or whatever to check that fact. So the point is that we get 1, and that's exactly how it should be. We now have both marginal probability distributions. One is this, py of y equals 1, and the other one is px of x equals minus log x. From this, we can get the conditional probabilities. So let's first ask, what is the conditional probability that y is equal to y given that x is equal to x? And then ask, what is the probability that x takes the value x given that y has taken the value y? When we talked about conditional probabilities earlier, we found that this is exactly how it is. So this first conditional probability is the joint probability distribution divided by the marginal in x. That gives minus 1 over y log x. And similarly, the other probability distribution is simply this divided by p of y. That's 1 over y. Of course, for both of these conditional probabilities, 1 over y or this over here, we must have that y is limited to this region and x is limited to this region. Now that we have the marginal probability distributions, we can do some more calculations. Let's ask over here, what is the average value of y squared, of the standard deviation in y, and similarly for x and x squared, and standard deviation in x? Now, of course, you remember that if we take any expectation value, whether it is of x or y, it is all of the same form. You take whatever is over here and you weight it with the appropriate probability distribution. So we can calculate the expectation value of the random variable y by taking y from 0 to 1. That's because we discovered that py of y is equal to 1 in this range. And so clearly the average value of y is a half, very trivial. The average value of y squared will be y squared into py of y, which is 1, of course, as before. And so this is y cubed over 3, which gives 1/3. If you remember the formula for the standard deviation, well, sigma y squared is equal to the average value of y squared minus the average of y squared, and so that's 1/3 minus a half squared, which is equal to 1 over 2 square root 3. If you want the average value of x, well then you have to take x and weight it with the marginal probability distribution in x, which is, as we discovered just a little while ago, minus log x. And so we need to do the integral x log x from 0 to 1. Of course, that's quite easily done, because if you integrate x log x, then this is what you get. You get x squared over 4 minus half x squared log x, and you have to evaluate it between 0 and 1. How do I know that this integrates to this? Again, the best way to do it is by guessing the answer and then simply differentiate this, and you'll see that you get minus x log x. So indeed, this is the correct integral of minus x log x. Once you take limits between 0 and 1, then as before, you will get 1/4. We can go on to the average of x squared. Here, the only difference is that you have 2 powers of x instead of 1 power of x. The integration is just only a little bit more complicated, but again, here is the answer. To check this, differentiate this with respect to x, and you'll get what's above over here. Take the limits between 0 and 1, and you will get 1/9. Again, it's a completely straightforward calculation. Similarly, if you take the standard deviation in x, well then it is this 1/9 over here minus the square of 1/4. Work that out. The square root then works out to square root of 7 over 12. Now let's move on to the last part of this question. We are asked to find the average value of x into y. So this random variable, which is x into y, we have now to calculate the covariance and the correlation. The correlation, you remember, is the same as the covariance, except that you have to divide it by the standard deviations in x and y. Just as in the case of discrete random variables, what we do is taking the expectation value of xy means that you take x into y and weight it with the joint probability distribution function integrated over x and y, but we've got plenty of practice with that now. X goes from 0 to y, and y goes from 0 to 1. Again and again, I remind you that the outside integral sets how far x can go. So x will go from 0 to y as y itself goes from 0 to 1. Work out the inner integral. This y cancel this y, and the only thing is the integral over x, which between 0 and y gives you y squared over 2. And so we are left only with this integral over y from 0 to 1. That, of course, is 1/6. And so we have the average value of xy equal to 1/6. Next, we can calculate the covariance. The covariance is the average value of xy minus the average of x into the average of y. These we have respectively from here and from here. So just do the subtraction, that's 1 over 24. And now the correlation of x and y is 1 over 24, this 1 over 24 divided by sigma x multiplied by sigma y. Work that out, and that's square root of 3 over 7, a positive number, which means that x and y are positively correlated for this joint probability distribution function. In both the examples that I just worked out for you, the joint probability distribution function was given. It was not derived. But we can sometimes derive this joint probability distribution function. Let's take the example, therefore, of trains arriving at a station, at which 2 trains can arrive. We will associate the random variable x with one train and the random variable y with the other train. Now let's say that train x has uniform probability of arriving at track number 1 in the time interval between 0 minutes and 30 minutes, while the train y has uniform probability of arriving at the second track in the time interval 10 minutes through 20 minutes. What we want are the marginal probability distributions as well as the joint probability distributions. Now, here one can assume that the arrival of one train has got nothing to do with the arrival of the second train. In other words, these two are uncorrelated with each other, and therefore the joint probability distribution is just the product of this into this. Let's write down a mathematical form for this marginal probability distribution, that is to say, the one in x. It can be written easily as this. So, for times before 0, there is no chance of the train arriving. There is no chance of the train arriving for times greater than 30 minutes, but between 0 and 30, there is equal probability. How much is that probability? Well, we know that the integral of the probability has to be 1, so integral of 1 over 30 from 0 to 30 is obviously equal to 1. And so this normalization constant has been adjusted to the value 1 over 30. We could leave this answer just as it is, but we can sketch it also. So if x is negative, the probability is 0. If x lies between 0 and 30, that probability is 1 over 30, and of course it's 0 beyond that. The area under this curve that I am indicating here is of course equal to 1. We can do exactly the same with the other train, which must arrive between 10 minutes and 20 minutes. Since the area under this must be equal to 1, Therefore, this height has to be 1/10. So this interval here is 10 minutes, and this is 1/10. Their product is 1. In terms of formulas, here's how you would write this. P of y is 0 if y is less than 10. It's 1/10 if y is between 20 and 10. And it's 0 if y is bigger than 20. What is the joint probability distribution function? Here's how to find that. We'll say that this is a constant, some constant c, provided that x is between 0 and 30, and y is between 10 and 20, and is 0 outside of this. Well, we can sketch this, but now we need two axes. We need the x-axis and the y-axis. And so it is in this rectangular strip over here that the probability is non-zero. It's non-zero, but what is the value? That we will find from this normalization condition, that p of xy integrated over xy is equal to 1. And now that's straightforward because this over here is a constant c, and dx dy integrated over this rectangular strip, well, that's just the area of this strip. The area of the strip is the width into the height. The width is 30. The height is 20 minus 10, which is 10. And so c is 1 over 300. Put this 1 over 300 here, and we found the joint probability distribution function as required. This was an exceptionally simple case because the arrival of one train doesn't have anything to do with the arrival of the other train. If that's not true, then this will not hold. We'll have something more complicated that depends upon the particular circumstances of that rail station. Let's now take a less trivial example of a joint probability distribution function. We are aiming darts at a board, as shown over here, and these are thrown randomly on this board which has radius a. Let's assume that those hitting the board are uniformly distributed as a function of radial distance. So, although you have aimed for the center of the dart board, yet your dart may have landed here or here or here or here or here, and furthermore, it could have landed here, 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 or here, here, here. In other words, both in terms of angle and in terms of radial distribution, there is randomness. Anyway, if we do assume that, then we have the probability of a dart landing at coordinate x and coordinate y is equal to a constant. Well, that constant, we could have called it c, but we know that the value of that has to be 1 over pi a squared because when we multiply by the area of the board, then we'll get 1 in that case. And of course, we are limiting ourselves to darts that have arrived on the board, and so obviously this p has to be 0 if this condition is not met. In other words, if that dart has missed the dartboard. We are now asked a very specific question. What is the probability distribution of darts in x? Now, of course, you know very well that in that case, we must integrate over y. In this integral, y takes all values from minus infinity to plus infinity. However, for most of this range between here and here, p is equal to 0. Now let's understand this using a diagram. So here is the center of the dartboard, the radius is a, this distance is x, and y is here, minus y is here. And we're going to integrate all the way from minus infinity to plus infinity, but with x being fixed. So if x is this, then the maximum value that y can take will be square root of a squared minus x squared, and the minimum value, as you can see from here, will be minus square root of a squared minus x squared. Now this integral is actually very trivial because the integrand is just 1, which means that the integral over y is 1 evaluated between this limit and this limit, which we write over here like this. And obviously, this is 2 over pi a squared into square root of a squared minus x squared. Now notice that if x is equal to plus a or minus a, then p is equal to 0. And of course, if x exceeds a, then also this is 0 because p of xy is 0 unless we are within that dartboard's range, within its radius. So this p is a function which takes its maximum at x equal to 0 and takes its minimum, that is to say 0, when x is equal to plus or minus a. That is to say, when x takes this value over here or takes this value over here. If we have calculated this correctly, then of course the integral of this marginal probability distribution ought to be 1. In other words, this should be 1. Is it 1? Well, actually, I'm going to leave this for you to do, but it's very easy. Just put x equal to a sine theta, in which case you'll have over here a squared into 1 minus sine squared theta, which is cos squared theta, and so the square root of that will be a cosine theta, and then dx is equal to a cosine theta d theta. Just do the integral and you'll see that it is equal to 1. Of course, if we calculate this marginal probability distribution, that is to say in y, it's exactly the same, except where there is x, such as over here, now there's y. And now for a final example. This goes under the name of Buffon's needle problem. So imagine that we have lots of parallel lines, this, separated by some distance which we will call capital L, and now from a height we throw a lot of needles or equivalently matchsticks. So here I've thrown a whole bunch of matchsticks, and you notice that some fall between the lines and some cross the lines, such as over here. So this match has crossed this line here. There's a second crossing here, third, fourth, fifth, sixth, seventh, eighth, and I'm marking all the crossings up till this very last one. So of the 28 matchsticks that were thrown, 18 crossed the line and 10 did not. Well, if I throw it again, then maybe out of 28 matchsticks, 11 will cross the line and 17 will not. This is a random process, and we would like to calculate the probability that a matchstick would cross a line. So here is a matchstick that did not cross the line. However, here is another matchstick that did cross the line over here. We're going to call the distance from this end of the matchstick to this lower line here, x. The distance between the lines is capital L, and the size of the matchstick, its length, is a, like over here. We will call this angle over here theta, and theta is going to take all values which will go from 0 when this matchstick is parallel to this line over here, and increase all the way from 0 and come back to 2 pi after making a complete circle. So the limits on x and theta are x going between 0 to L, and theta going between 0 and 2 pi. Obviously, this length over here is a sine theta. The tip of this matchstick is here, and it will barely cross this upper line, and in that case, then of course this remains a sine theta. We're keeping theta fixed, but then this distance over here, from here to here, will be L minus a sine theta. So this will be the minimum value of x for crossing the upper line. Now let's look at this same diagram and get a little bit of calculation done. So as I said earlier, x will lie between 0 and L. Again, remind you that x is the distance from this tip of the needle to the line below, with this tip being anywhere between 0 and L with equal probability, and with equal probability for any value of theta that lies between 0 and 2 pi. We will call that probability density of it landing between x and x plus dx and between theta and theta plus d theta as c. Of course, that means that we have to have a normalization, so that if we integrate over all values of x and all values of theta, then we should get 1. That means we have to integrate x from 0 to L and theta from 0 to 2 pi, and that has to be 1, which means obviously that c is equal to 1 over 2 pi L. So that fixes the normalization constant that we have over here. Now, let's consider the specific situation where the upper line is crossed. That means theta will have to be between 0 and pi. Obviously, if theta is down below over here, then it cannot cross the upper line. Now, the other condition is that x obviously has to be less than or equal to L, but then it has to be greater than this, L minus a sine theta. So what we need to do is to integrate the probability density for all values of x that lie between L minus a sine theta, this is the lower limit, and between the top limit, which is L, and integrate over all values of theta from 0 to pi. This is p, which we can pull out of the integral. This 2 over here comes about because we're just considering the upper line. What about the lower line? Well, the lower line will be crossed with equal probability as the upper line. So now we can trivially do the inner integral. That inner integral over here is just x between L and L minus a sine theta, which is a sine theta. So we get 2a sine theta, and now theta is integrated between 0 and pi. Again, I insist that this is pi and not 2 pi because we've already compensated with the 2 over here. Good. So now we get 2c into 2a because this integral of sine theta going from 0 to pi is just equal to 2, as you can trivially verify. And so we get this answer, 2a over pi L. And that's equal to the probability of crossing either the upper or the lower line. We've got, in fact, a formula for pi. Isn't that quite amazing that pi should be equal to 2 over p into a over L? And I remind you that a has to be less than L. That is to say, the length of the matchstick has to be less than the distance between the two lines. This can be very easily simulated on a computer, and in fact people have done it using Mathematica. It's a ready-made program. Here is a case where 20 needles were thrown, and you can see that these red ones cross the line, some line, whereas the green ones miss the line. In this particular case, of the 20 needles that were thrown, 9 crossed the line and 11 missed it. One can adjust parameters over here, and what I did was I took A over L to be 5 over 6. You can take it to be 1 over 3 or 9 over 10 or whatever, but A has to be less than L. That is to say, the length of the matchstick or the needle has to be less than the distance between the two parallel lines. Anyway, if we apply our formula, we get a value for pi which is not very good, but it is still in the correct order of magnitude range, 3.704. Well, what if I take more needles? In this case, I've taken 100 needles and found that 50 of them crossed the line and 50 of them missed the line. Again, if we take our formula, pi is equal to 2 over p into A over L, you get a value for pi which is a little bit better, 3.334. Of course, this is not the way to get the exact value of pi, because you would need to take an infinite number of needles and throw them an infinite number of times, and certainly there are much better ways. Anyway, I hope you found this interesting.